Okay guys, the next topic is the ideal gas, a model, or we call it the kinetic theory of gases. We discuss a little bit about it in the class, we discuss about the assumptions of kinetic theory of gases. Here I will repeat those assumptions again, like the assumptions of kinetic theory of gases. Theory of gases. As I already mentioned that there are a few assumptions. The first assumption is, I will list it here. Gases are composed of particles called molecules. Gases are composed of particles called molecules. This is the first assumptions of kinetic theory of gases. The second assumption is the molecules are in random motion. The molecules are in random motion. And obey, during this motion they obey Newton's laws of motion. Newton's laws. This is the second assumption. The third assumption is, third one, the size of molecule is very small. The size of single molecule is very small as compared to the volume occupied by the gas. This is the third assumption. The fourth assumption is molecules collide with each other as well as with the wall of the container. Like the molecules collide with each other as well as with the wall of the container. But remember that the time between two collisions is very small. And the fifth and the last assumption of the kinetic theory of gases is all the collisions are elastic. All the collisions are elastic. What it means? It means that is the kinetic energy and linear momentum. The kinetic energy and linear momentum of molecules remain conserved during collision. Like the collision is elastic. By elastic collision we means that the kinetic energy before collision will be equal to the kinetic energy after collision, and similarly the linear momentum before collision of the molecule will be equal to the linear momentum after collision. These was the fourth assumptions, 5 assumptions of kinetic theory of gases. Next, we will, on the basis of these assumptions, we will calculate the pressure. We can call it pressure of a gas. On the basis of kinetic theory. On the basis of kinetic theory. This is the name of the topic. We will calculate the pressure, or the pressure exerted by these molecules during collision on the wall of the container, on the wall of the system in which these molecules exist. For this one, we consider a cubical container. Let's suppose we have a cubical container. By cubical I means the length of each side is same. So here we have this cubical container. So let's suppose this is the x-axis, this is y-axis, and this is z-axis. This is a cubical container. Now we consider that there are many molecules inside this container, but here for simplicity I will consider only a single molecule of mass m. I consider a single molecule somewhere in this container of mass m, and I suppose that it is moving with velocity v. Let's suppose this is the velocity v of this molecule. Now this velocity has three components. Now if I decompose this velocity into its component, because this is a three-dimensional plane now, so this velocity has three components. One is vx, the velocity component along x direction. One is vy, the velocity component along y direction, and the third one is vz, which is the velocity component in z direction. Like if I suppose that this particle or this molecule is moving in this way, then it is also moving along x-axis, it's also moving along y-axis, and it is also moving along z-axis. So we have three velocities. This is the resultant velocity v. So this velocity has three components. One is vx, which is the component of velocity along x-axis, and then we have another component which we call it vy, which is the velocity along y-axis, and this is the velocity along z-axis. Now for simplicity, I suppose that I call these sites specific names. Suppose this is one wall of the container. I represent this wall by A, B, C, and D. This is the wall A, B, C, D. Okay, and this is another wall. I call it A prime. This point is B prime. This point is C prime, and this point is D prime. So we have two walls now. One is this wall, okay, and one is this wall. One is this face and one is this face. This wall I call it A, B, C, D, and this wall I call it A prime, B prime, C prime, and D prime. Now I suppose that this molecule is only moving along x-axis with velocity vx. I can write it here. I say that suppose I suppose that this molecule is moving along x-axis. Suppose that this molecule is moving along x-axis and makes a collision with this one and makes a collision with wall A, B, C, D. I can draw this wall here again. Suppose this is the wall A, B, C, D. This is A, this is B, this is C, and this is D. And this molecule, which is moving along x-axis, make a collision here with this wall. Okay. Now the molecule is moving along x-axis, so it has velocity Vx and it has mass m. So its momentum along x-axis will be mvx. This is the momentum of molecule before collision with the wall. Like this molecule with mass m and velocity Vx moving in this way, so it has momentum mvx before collision. Now once it collides with this wall, what will happen? It will bounce back. So when it collides with this wall, okay, this is A, B, C, and D. When it collides with this wall, after collision it will bounce back in this way. So its direction of velocity is changing now. Before the direction of velocity was this one, now its direction of velocity is this one. So after collision the momentum will be, after collision the momentum will be minus mvx. Here this negative sign represented the direction of momentum or the direction of velocity is now changing here. Before the direction of velocity was this one, now the direction of velocity is this one. So this direction I call it negative and this direction I call it positive. I can say that this is the x-axis, so here it moved towards positive x-axis, here it moved towards negative x-axis. So the direction is changing now. So this is the momentum before after collision and this is the momentum before collision. Now the change in momentum. During this collision there is a change in momentum, so we have to find the change in momentum. The change in momentum which I represent by delta px, but this is the change in momentum along x-axis, so I call it delta px. So this will be equal to, we are normally represent the change by final momentum minus initial momentum. We can say that momentum before collision, before momentum after collision minus momentum before collision, like momentum after collision, okay, minus momentum before collision. This will give us the change. Now delta px, change in momentum of the molecule will be momentum before collision, after collision is minus mvx, this one, and then we have a negative sign here, and then momentum after before collision are initial momentum, which is mvx. So the change in momentum delta px will be minus 2 mvx. I consider this container to be cubical, so the length of each side of this cubicle is same, so I call it this length from here to here, this is L, from here to here this is also L, and from here to here this is also L. So the length of each side is the same. This is the change in momentum of molecules. Okay, now we already discussed in the assumptions of kinetic theory of gases that the collision will be elastic. So it means that since the collision is elastic, I can say that the collision is elastic. Collision is elastic and the momentum will remain conserved. Momentum will remain conserved. Okay, so the change in momentum given to the wall. So the change in momentum given to the wall will be delta px, which will be equal to 2 mvx. Okay, here we have a negative sign, so here will be the momentum will be positive because the momentum is given by the molecule to the wall, and this was the change in momentum of the molecule. So the momentum, the change in momentum given to the wall will be 2 mvx. There will be no negative sign because the momentum is now changing. So the total momentum will remain the same. So if I add these two, I will get the initial momentum. So here we have no negative sign. Now next we have two walls now. Here we have two walls now. One is wall A, B, C, D, and one is wall A prime, B prime, C prime, and D prime. I suppose that a molecule started from this wall. Okay, it moved along this way, along x-axis, collide with this wall A, B, C, D. After collision, it will bounce back and return to this wall again, A prime, B prime, C prime, D prime. So the time taken during this complete round trip, like moving from this wall A prime, B prime, C prime, D prime to wall A, B, C, D, and then again from wall A, B, C, D to wall A prime, B prime, C prime, D prime, it will be like the time taken during one complete round trip. By round trip I mean is, suppose I will plot the two walls again here. This is one wall. Okay, like a molecule started from this wall A prime, B prime, C prime, D prime, move in this way, collide with this wall A, B, C, D, and then again after collision it will bounce back and reach to this point again, A prime, B prime, C prime, D prime. So the time taken during this complete round trip, it will be delta t, I represent it by delta t, which will be equal to 2L over Vx, because we already know that we have the relation for the velocity is v is equal to displacement distance over time. This is the velocity or speed. We have displacement over time. Now if I calculate t from here, then we have t is equal to s over v. Now the particle is moving along x-axis, so its velocity will be vx. Okay, velocity will be vx. So its velocity will be vx. Now the distance covered, how much distance it will cover during this round trip, because we have this length which is L, so it is moving on this way, reach to this one, it cover a distance L, and it's bounce back and again move to this point, so it will cover again a length of L, 2L. So the total distance cover is 2L now. So distance will be 2L. So the change in time delta t will be equal to 2L by using the value of s divided by velocity is now vx. This is the change in time. Next we have to calculate the rate of change of momentum of the molecule. Now the rate of change of momentum of molecule, it will be rate of change of momentum means delta px over delta t. Okay, this will give us the rate of change of momentum. So we have delta px, which is already 2mvx. Okay, 2mvx from this relation, delta px, which is 2mvx. So I put, instead of delta px, I put 2mvx, or delta t is now 2L over vx. 2L over. Now 2 cancel with these 2. So we have this rate of change of momentum delta px over delta t, which is equal to mvx square over L. So I will stop my video here. In the next video I will proceed from this point. Thank you.